We can describe the elemental composition of a compound in a couple of different ways. If we describe the simplest ratio of elements in a given compound, that is known as the empirical formula. If we describe the actual number of, or the actual ratio of elements in a compound, that is referred to as the molecular formula. And of those two, the empirical formula kind of dictates or drives how the molecular formula is going to be. It will usually be some whole number multiple. The molecular formula will be of the empirical formula. So to determine the empirical formula, we need some given information to start with. We need to either know the actual masses of the elements that are present in the compound, or we may be given the percentage composition. And if we're given the percentage composition, there's one crucial step that we need to do at the very beginning, and that is to make a statement that we're assuming that the total mass of the compound, of the sample that we have, is 100 grams. By making that simple statement, we legitimately go from the percentages that we're given to start into grams, for which we can begin our calculation then. Once we have the grams, the mass of each element, then what we can do is convert to moles using the molar mass for those elements. And then we want to compare those three, or however many there are for elements, compare those mole numbers. Whatever the smallest mole number is, that's what we will divide into all of the mole numbers. And what that's going to give us, hopefully, is a whole number ratio. And those whole numbers become the subscripts for each respective element, and that's our empirical formula. Now, I said ideally, it will be a whole number. There may be instances where you get a fractional equivalent like 0.5 or 0.25, even maybe 0.33 or 0.67. Any fractional decimals that you get should be equivalent to a common fraction, like a half or a quarter, a third or 2/3. And so before we take those quotients and use them as subscripts, we have to get rid of any fractional decimal values. So whatever the fraction is that you get, for instance, if you ended up with a 0.5 for one of those quotients, you would need to multiply not only that quotient, but all of them by 2, so that you eliminate the 0.5. If you get one that ends in 0.25, then you have to multiply everything by 4 to clear that out. So if we take a look at this example, a 5.325 gram sample of methyl benzoate, which is a compound that's used in the manufacturing of perfumes, contains 3.758 grams of carbon, 0.316 grams of hydrogen, and 1.251 grams of oxygen. And the question is, what is the empirical formula of this substance? So here we are given grams, so we don't have to make this initial statement because we're already in grams. So we can begin by using the molar mass of each element. Notice that when we are using the molar mass, we are using the atomic molar mass. If it's a substance like hydrogen or oxygen, which is naturally diatomic, we are not talking about the diatomic molar masses here. So that's an important point to note. If you compare those three mole values, you can see that the smallest one is 0.07819 for the oxygen, and so we will divide each of those mole values by that 0.07819. And the quotients that you see are very, very close to whole numbers. If you get a value that is not exactly on a whole number, but it's like these where it's within hundredths or maybe even thousandths, then it's okay to round it off. But if you get something that's like 0.1, you want to go back and check your math, check your numbers, because really you should get those quotients coming out to, so long as you're using proper sig figs. If you're only for some reason using one sig fig in those mole values, then yeah, you're probably going to run into some issues. Generally speaking, you'll probably always have 3, if not 4 or more to deal with there. So as you can see here, then we would take those whole numbers and use those as our subscripts, and we get C4H4O for the empirical formula for methyl benzoate. Next, we have cyclohexane, right? A common organic solvent, and we're told it's 85.6% carbon, 14.4% hydrogen by mass, and we're asked what is its empirical formula. So here we are given percentages, so the first thing that we need to do is make the statement assume total mass will be 100 grams. What that does is it green lights us to now say, okay, 85.6% of 100 grams is simply 85.6 grams of carbon, and likewise 14.4 grams of hydrogen. Realistically, you could choose any mass for the total mass assumption, but 100 makes the most sense because you're dealing with percentages. That way you just change the percent sign for units of grams. Using molar masses, we see that the smaller of the two mole numbers is 7.127, so we divide both by that 7.127 moles, and that's going to give us a nice 1:2 ratio, and so the empirical formula for cyclohexane is CH2. Now you might wonder, well, how is it that we would get these masses of these different elements, or the percentage composition? One of the analytical methods that we can use to achieve this data and this information is called combustion analysis. And as the name indicates, it involves burning the sample, burning it completely. And for hydrocarbons, if you have complete combustion, you're going to get two primary products, carbon dioxide and water. So what happens is, and you can follow in the schematic here, you have your sample in a furnace, it's combusted, and so those products then are carried through the analyzer by a stream of oxygen, usually some carrier gas. And so as it passes through the different chambers, each chamber contains a material that will absorb either water or carbon dioxide. And so what happens is you know the mass of those materials before the combustion takes place and they absorb the byproducts, and then you measure them afterwards. So what you get is the mass of water that was produced and the mass of carbon dioxide that was produced. And then we can use stoichiometry to help us figure out how much carbon and how much hydrogen was present. And we can even use this when we have organic compounds or hydrocarbons that have other elements like oxygen or nitrogen in them. So let's take a look at some of those examples. To determine the amount of carbon, we have to start with the amount of carbon dioxide that was produced. And so stoichiometrically, we need to determine, what is the mass of carbon that's present there. So you first have to convert 2 moles of carbon dioxide using the molar mass, then use the ratio of 1 carbon atom for every carbon dioxide molecule to get the moles of carbon that was in that sample, and then use the molar mass of carbon to get to the mass of carbon. Likewise for hydrogen. This time we're going to start with water's mass. Use its molar mass to get the moles of water. Then the ratio here is 2 moles of hydrogen, or 2 hydrogen atoms per water molecule. So it's a 2-to-1 ratio. And then use the molar mass of atomic hydrogen to get to the mass of atomic hydrogen that you had in the original sample. Again, it's not diatomic hydrogen that we're dealing with here. If there's a third element, like oxygen, nitrogen, something else, then we have to do a little bit of subtraction. Okay, there's no substance in most combustion analysis instruments that will absorb those additional elements. Plus, oxygen is frequently used as the carrier gas, so you're introducing oxygen to the mix. So that wouldn't be very easy to do, in the same manner. But what we then have is, to find the mass of that third element, what you have to do is to subtract out the masses that you know for the carbon and the hydrogen from the total mass sample, and that will give you the mass of your third element. So here's an example, all right, involving combustion analysis, and we see that we have a 10-gram sample, all right, and that 27.42 grams of carbon dioxide was produced when it was combusted, as well as 22.46 grams of water being produced. So for each of those, we have to follow those schemas that we just looked at. For the carbon dioxide, we convert to moles, all right, and then we take the moles carbon dioxide, use the mole ratio to convert to moles of carbon atoms, and then from there, that's going to be the number that we need to use for the empirical formula portion. And in this case, it's not necessarily, aside from double checking our work, not absolutely necessary to convert to grams. but when we have 3 or 4 elements, then we will need to finish it out and determine what is the mass of the carbon that's present. So in this case, it would be 7.48 grams. Do the same thing for water. Convert to moles of water, then get to moles of hydrogen atoms using the mole ratio. Okay. And again, that 0.623 moles carbon, 2.50 moles hydrogen, those are the numbers we're going to be interested in to get that empirical formula. Okay. Carrying the hydrogen calculation through, we see that the equivalent there is 2.53 grams of hydrogen. And so if we added those two masses together, we see that we get 10.01 grams, which is very, very close to what we originally started with and was given to us. The discrepancy there probably lies in the fact that we only use 3 sig figs for the molar masses. Okay? But be that as it may, if we look at these two, 0.623 and 2.50, clearly 0.623 is the smaller of the two. So if we divide both of those mole numbers by 0.623, we get a 1 to 4 ratio. And so our empirical formula would be CH4. Now, if you're following along in your notebook, the companion that goes along with this lesson, there are 3 more examples. You see the first one here with masses of carbon dioxide and water, respectively given. And then you also have the empirical formula. So treat that empirical formula column as your self-check answer key. Use the masses of carbon dioxide and water that were provided to you. Go through that same process, practice it, and then when you get to the end and get an empirical formula, check it against this next to last column and see if you got that correct. All right, so let's try a combustion analysis problem when there are 3 elements present. So we've got a 15-gram sample of a compound that contains carbon, hydrogen, and nitrogen. All right, analyzed by combustion analysis. The sample produced 29.3 grams carbon dioxide, 20.8 grams water, and we're asked to find the empirical formula of the unknown. So notice it doesn't tell us anything about the nitrogen, so we're going to have to deduce that based on what we're given. So we start with the mass of carbon dioxide produced, and we go through the same steps, convert to moles of carbon dioxide, convert to moles of carbon, and then here we definitely are going to have to go to grams of carbon because that's how we're going to be able to determine how many grams of nitrogen were present in that sample. Do the same thing for hydrogen, starting with the amount of water that was produced, convert to moles of water, then to moles of hydrogen atoms, and finally 2 grams of hydrogen atoms. And now that we know how many grams of carbon, how many grams of hydrogen are present, now we can calculate the grams of nitrogen by taking the mass of the entire sample, 15 grams, minus the 7.99 grams of carbon, minus the 2.34 grams of hydrogen, to find that we have 4.67 grams of nitrogen. Okay? So now we know the mass that was present, but to get the empirical formula, we need to know the moles that that's equivalent to. So we use the molar mass of atomic nitrogen to get the number of moles that we got, which is 0.334. All right, so cleaning this up a little bit, let's focus on just those mole quantities there. The smallest mole quantity we have is 0.334 moles, so we're going to divide all 3 by that. For carbon, we get 1.99, which is close enough to 2 for us. For hydrogen, 6.95, close enough to 7. We'll call that 7. And then the last one for nitrogen is obviously 1. So putting those together, we would get an empirical formula of C2H7N. Okay? If we can do it for 2 elements, we can do it for 3 elements, we could even do it for 4 elements, depending on what's provided. So here we take the compound quinine, which was used to treat malaria. And we're also told its molar mass, which is interesting. We haven't seen that before. We'll see if we need it or not. And we're told it contains the elements carbon, hydrogen, nitrogen, and oxygen. 0.487 grams of quinine is combusted and found to produce 1.321 grams of carbon dioxide, 0.325 grams of water, and 0.0421 grams of nitrogen. And we're asked to determine the empirical and the molecular formulas of quinine. So that's the extra piece. And if you're thinking about things here, up until now we've just been asked for the empirical formula, and we were never given the molar mass. Now we're asked for the molecular formula as well, and we're given the molar mass. So maybe there's a connection there, and that can give you a clue as to where that molar mass is going to come into the picture. But before we get to that, got to figure out the simplest ratio. So another empirical formula problem. Start with the amount of carbon dioxide, convert that into moles carbon dioxide and moles carbon, and then convert that into grams carbon. Same thing for hydrogen coming from the water. Convert grams water into moles water, then convert that into moles of hydrogen atoms, then convert that into grams of hydrogen. All right. Now, we determined the mass of carbon and mass of hydrogen, and if you read the problem again, we're told that we've got 0.0421 grams of nitrogen, but it's molecular nitrogen, it's N2. So we do have to work with that number a little bit. We've got to convert it to moles. So here, because it is N2, it is molecular nitrogen, we have to use the diatomic mass, which is why you see the 28.0 grams used there. Then we need to use our mole ratio, which for every 1 mole of nitrogen molecules, we get 2 moles of nitrogen atoms. And then we see that we get 0.00301 moles of nitrogen. Okay, and that's going to give us the final, well, not quite the final, excuse me, not quite the final. We're going to need to use that number when we calculate the empirical formula. Converting that to grams using this time atomic nitrogen's molar mass. Again, be careful as to which molar mass you're using in each step. And we get 0.0421 grams of nitrogen. Now that we have the grams of nitrogen, now we can, by subtraction, get the mass of the oxygen that's present. So 0.487 grams, that was the total sample mass of quinine, minus 0.360 grams of carbon, minus 0.0366 grams of hydrogen, minus 0.0421 grams nitrogen, for a grand total of 0.0483 grams oxygen, which if we convert to moles, because we're going to need that to determine the empirical formula, comes out to 0.00302 moles oxygen. Now that we have those 4 elements and their mole quantities that are present, now we can look at these and determine what is the smallest mole value that we've got. And you want to be careful. Make sure you pay attention to decimal places, the magnitudes of the values. Okay. The smallest mole number we've got is the one that's coming from nitrogen, 0.00301. Okay. And so when we divide that out, carbon comes out to 10, hydrogen comes out to 12, nitrogen comes out to 1, and oxygen pretty much comes out to 1 as well. So putting it all together, the empirical formula, the simplest ratio formula for quinine would be C10H12NO. Right? So that's the first part of the answer, determine the empirical formula. Now we need the molecular formula. Well, we know that the molecular formula is going to be a whole number multiple of the empirical formula. And so it stands to reason that this molar mass that we have should be the same whole number multiple of the mass of the empirical formula. So we'll call that the empirical mass. So if we calculate that, 10 times the mass of carbon plus 12 times the mass of hydrogen plus 1 times the mass of nitrogen, 1 times the mass of oxygen, we find the empirical mass here to be 162.1, okay, depending on how many sig figs you're using. So we would divide that into the molecular, the molar mass, and we find that we get a value of 2. So now that becomes the multiplier for all of the subscripts in the empirical formula. And so the molecular formula for quinine would be C20H24N2O2. So the question then that might peak in your brain is, okay, well, how exactly do we know what the molecular weight's going to be? Okay, we talked about combustion analysis to get the data that we need for the empirical formula, but what about that other key piece of information? Well, this is something else that can come from mass spectroscopy. Remember that in mass spectroscopy, you inject the sample, it's vaporized, and then it's bombarded usually with X-rays, but it's a rather violent process to try and knock off electrons and create ions so that they can be propelled through the instrument. Well, besides just ionization, sometimes you have fragmentation, which means the bonds actually get broken. You get parts of the molecule breaking off. And so that's what you'll see a lot of times. You'll see these multiple peaks, okay? But we're interested in pretty much the intact molecule with all of its bonds still there. So if you think about it, the best case scenario for a sample going through is that all that gets knocked off is an electron. It gets ionized and that's it. So when we look at all the peaks, all the major peaks, okay, the minor peaks are due to different isotopes of the component elements, but you want to focus on the major peaks. Whatever the heaviest peak that you see is, major peak that you see, that is going to be your unfragmented sample. And so for all intents and purposes, that is your molecule. And so we see that for methyl benzoate. Remember, we looked at that example a little while ago. It was used in perfumes. Okay, the unfragmented sample, the major peak here on this mass spectrum is 136. So that tells us that the molar mass of methyl benzoate is actually 136 grams per mole. So if we use that now with the empirical mass that we can calculate from C4H4O, which comes out to a little over 68, divide those two numbers, and again we get 2 here. So that means the actual ratio of carbon to hydrogen to oxygen in methyl benzoate is 8 carbons, 8 hydrogens, and 2 oxygens. So we get the molecular formula. If we do the same sort of thing here for cyclohexane, remember that empirical formula was CH2. And as we examine the mass spectrum, we look at the major peaks and we see the heaviest one is right here, just about 84. Okay, and so if we take the molar mass of 84 and we divide that by the empirical mass, 1 carbon plus 2 hydrogens would be a little over 14. Divide that out and we get just about 6. So if we multiply 6 times the subscripts that we have in the empirical formula, we find that the molecular formula for cyclohexane would be C6H12.